Good morning. My name is trshrivastava and today we are here to discuss about echo generation and echo removal using comb filter. These are the contents of this PPT. What is comb filter? What are the types of comb filter, which include feed forward comb filter and feedback comb filter? What are the applications of comb filter? Where we see unwanted comb filters in daily life, implementation in MATLAB, results and conclusion. First of all, what is a comb filter? So in signal processing, comb filter is a filter which is implemented by adding a signal with itself along with a delay. Suppose X is a signal, a sound signal, and if we want a comb filtered output of X, what we do is we add X with a delay D to itself. That is X of N plus X of N minus D. Okay. For better example, I'll show you some pictures that will be helpful. So here, let us assume the purple, yellow and green. These three combined make a sound signal X. Okay. Again, this 3 is added with itself, X. Okay. So X plus X, what we'll get is this kind of frequency domain output. This is with 0 milliseconds of delay. What happens is this is a random frequency output with which should be obtained because of this, because of the addition of this. What will happen is all the phases are coinciding with each other, and hence the amplitude should be multiplied by 2. Okay, but when we do this, what we are going to do is X is as it is, but X is given a delay, suppose D. Okay, suppose a delay of 10 milliseconds. So this is what is going to happen. Now as we can see, the purple part, the top purple part and the bottom purple part are completely out of phase. Okay. Again, what is second, the yellow part is in phase, completely in phase. So what will happen is these two will add up to each other and get 2 times the amplitude, whereas purple will get cancelled out. And the green part with this blue is basically just out of phase, just a little phase difference, and hence they will give a muffled effect. They will not completely add, neither they will completely subtract to each other. Okay, so when we see this addition of these two in frequency domain, what we are going to see is this. You can see this is a comb like appearance. It is having a comb like appearance. Why is this so? So as you can see, these tips, the tips that are low, that is near the 0 line, 0 x-axis, this is formed because these points, these peaks, lowest peaks are formed because of the purple part. What happens is these two are completely out of phase and hence they add up to 0. Okay, these two had same amplitudes, but they are in opposite phase and hence they will add up to 0. These zeros are shown here, shown at the lower peaks. Now the upper peaks, the top peaks are found because of the green and this yellow part, because these two are in complete phase. So what happens is their amplitude is multiplied by 2. So the topmost parts are because of these parts adding up. Now the parts which is slightly out of phase will form all the rest frequencies that are available in this frequency domain. So, okay, so now you can see addition of X with itself with a delay of 10 milliseconds will give you a comb like structure. This is what we call comb filtering. Okay, now we'll see the types of comb filtering. So basically there are 2 types of comb filtering: feed forward comb filtering and feedback comb filtering. So feed forward comb filtering, what we do with feed forward comb filtering is we have of X of N, we have a starting signal and we apply it some delay along with the attenuation function, attenuation constant. We multiply the attenuation constant, add it up with X of N and we get Y of N. As you can see, this is the mathematical equation of feed forward comb filter. What's next is we take a Z transform of it, we make a transfer function out of it, then we substitute Z with e power j omega and we get the magnitude response. This is the final magnitude response which is plotted here in the form of comb. Okay, So let me tell you the most basic function of feed forward comb filter is basically this is used to add echo to a signal. And this is in very crude terms, and you will be seeing this kind its application in the code that we'll see later. Next we have feedback comb filter. What we get what happens in feedback comb filter is we have y of n, we apply delay to y of n, we apply attenuation factor to y of n, we add it with x of n to get y of n again. Okay, this is the mathematical equation of feedback comb filter. And the later procedure is constant. We take z transform, we make transfer function out of it, we substitute z, and we get a magnitude response. This is the magnitude response that is plotted over here in the form of comb. Okay, so in the basic crude terms, the application of feedback comb filter is basically used to remove echo from a signal. Okay, this is also what we will see in MATLAB implementation later on. Now applications. Basically, what are the applications of comb filter? Let us study that. What are the desired applications of the comb filter? Okay, so cascaded integrator is basically a aliasing filter that is used. Okay, so we have heard about anti-aliasing filters in many of the communication systems, and comb filter is used in one of those as a cascaded integrator. Next we have 2D and 3D comb filters, which are implemented in hardware for PAL and NTSC as television decoders. These are the types of television decoders that is used for television communication to make sure that the frequencies of two different channels don't add up to each other, and for it we use comb filters. Again, there are many various types of applications of comb filters in audio signal processing. We use it for getting a delay, flanging effect, and also we use it for creating a detailed waveguide synthesis. Now, let us see some unwanted comb filtering. So for understanding some unwanted comb filtering in daily life, what we can assume is, suppose we are in a concert where 1 and 2 are basically two loudspeakers, and position A, B and C are seats where people will be sitting. So let us suppose first you are sitting on position A. For position A, the speakers 1 and 2 are at equal distances, and we know that speaker A and B are playing the same thing. Let us assume X. Okay, it is placing the same signal X. So for A, the signal will travel the same distance, and for A it will be same. But when we go for B, the signal from loudspeaker 1 will be traveling less, whereas signal from loudspeaker 2 will traveling more. This will create a phase difference between the two signals, and hence B will hear something different than A. Also for the C, the situation will be same such as B, only where one will be the signal from loudspeaker 1 will be traveling more distance than loudspeaker 2. Okay. So because of this, the listener will hear a mixture of direct sounds and reflected sounds. Okay, so one of the sound will take longer path, and it will constitute of a delayed version of the direct sound. Now let us move on to the implementation part. So this is MATLAB, and here I have implemented the code. Okay, so first of all, starting, what we did is we took input of the file that we want to add echo in. It is a WAV file, and audio read. This is a function that is used to read the audio file, and this is a part of audio processing toolbox of MATLAB, which is an inbuilt toolbox in MATLAB. We created time array for plotting purpose. We took p origin. P origin is basically a function that we will use for playing the audio. This is also part of audio processing toolbox of MATLAB. We take n, which is the length of x. X is the signal that we took. A is the attenuation factor, which we saw in here. This alpha is the attenuation factor, and this is termed as A in the MATLAB code. D is the delay in microseconds that we will be giving to our signal. Y is basically a zero array. We want an output array and we're creating a zero array beforehand so that there are no errors in future. X of n is a padded array. We make x of n as a padded array of x so that the length of x of n and y of n is same. We want same dimensions of both this. Now as you can see, this is the feed forward comb filter mathematical equation. Okay, and you also see there are many more terms that I have used in this equation. Why is this used? Now you can see that what I have done is basically I have added the various numbers to d, the delay, and this is basically the same term as this term but with different delays. What I did this is for I was not getting the echo satisfactory echo that I wanted, and for this I did this multiple times to get a satisfactory echo. Okay, now audio player, this is the function that is used for audio playing, for playing the audio. Okay, we took numerator with the length of n, we took denominator, we took a frequency response of the filter using this function. Okay, then we plotted. Absolute is basically the magnitude and angle is the phase of the final output that we are getting, the y of n. Let us play and see. As you can see, this is the magnitude in the form of comb and this is the phase, and you see we are having multiple frequencies and hence this is so thick. These are multiple frequencies that are present there. Now let us hear what we have done. This was the original signal. Again let us play it. And now we will be playing the echoed signal. You can see multiple. Now let us move on to the echo removal part of the code, which is basically a different code but the same thing. Now as you can see, the code is basically the same thing. What are the very few changes is we take y of n instead of x of n and we make it as an array of x. Okay, another change is this is basically the mathematical equation of feed back comb filter, not feed forward comb filter. As you can see here, see, this is for feed back comb filter, which is used for removing the echo. Next difference is z. Z is basically same as y, but what is it? This is basically just a amplitude multiplication for increasing the volume of the output, which y was not giving me the satisfactory volume, and for increasing the volume I did is multiply it with 15. The rest of the part is same, so let us run this. You can see magnitude and phase, we got a very clear term and they are basically identical, and we got it clear, a single frequency. Okay, let us hear what we have got. You hear multiple hellos. Okay, let us hear it. Now let us hear the output without the echo. You see only one hello. Only one hello. So this was the complete implementation as well as explanation of echo addition and echo removal using comb filter. Thank you.